Welcome to the Astrophysics Podcast. This past month has been graduation season at Purdue, with all our hardworking graduates dressing up in wizard robes and square hats, getting their name called as they walk across the stage. It's an old tradition, and it's an attempt to convey the sheer magnitude of the work they've put in over the past 4 years. A 2-hour ceremony really doesn't do it justice. And the graduates with the most elegant wizard robes and the most fancy hats of all are the PhD students. Earning a doctoral degree requires a lot of hard work and commitment. Between the bachelor's, master's, and PhD, that's about a decade of your life devoted to academics. And the PhD is nothing like any degree before it. For a PhD, it's not good enough just to study hard and get all the right answers. You have to make progress in a field, doing research that no one on Earth has ever done before. It's a totally different beast, and the PhD graduates deserve to be recognized for their outstanding achievements. This year's commencement was a first for me personally. What I mean by that is I graduated my first PhD student. I attended commencement and I was able to walk on stage with him as his name was being called and put his doctoral hood over his head, signifying the moment he can be now referred to as Dr. Mandal. One thing that's different about getting your PhD as opposed to a bachelor's degree or even a master's is the relationship you have with your PhD advisor. The advisor-advisee relationship is everything when you're a PhD student. Your advisor is important because they know what topics are new and interesting, what's been done before, and what types of research will have the most impact. Your advisor is there for you every step along your journey to a doctorate. When you get your PhD, it's almost a more gratifying moment for the advisor than it is for the student. There are many years of mentorship paying off and seeing a new scientist brought into the world. I know I had a big smile on my face when I hooded Soham. So now that he's earned his PhD, this week I decided my guest today would be Dr. Soham Mandal, who will be starting a postdoctoral research position at the University of Virginia this fall. Dr. Mandal has done incredible research in supernova remnants, writing his own three-dimensional fluid dynamics code to evolve supernovae over thousands of years to compare what they look like at these late stages with real observational data. Another fun fact about Dr. Mandal is that while doing his research, he also inadvertently designed the logo for the Astrophysics Podcast. You might have wondered exactly what that image is that I used for the logo. Is it a star? Is it a supernova? Actually, it's sort of both of those things, but in reality, it's the output of Soham's hydrodynamics code, which was computing the behavior of a supernova as it expands for centuries and collides with the surrounding gas. We're going to talk with Dr. Mandal about what supernovae look like after centuries of expansion, and I'm sure we'll also ask him about what it's like to get a PhD. I'm Paul Duffel, and this is the Astrophysics Podcast. All right, so let's get started. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Soham Mandal, who recently got his PhD here at Purdue and will be starting a research position at the University of Virginia this fall. So, Dr. Mandal, thank you for joining my podcast.
Hey, Paul. Thanks for having me. I'm thrilled to be here.
You got good. You got my note about what you're supposed to say after someone says thank you for being on my show. So good. So getting this out of the way really the first thing is, of course, you just got your PhD here at Purdue, and your thesis advisor was somebody that people may know.
Yeah, they might. Just might.
Just me. So, and it's, it was an exciting thing for me to be able to hood my first PhD student. And now that you are Dr. Mandal, I get to have you as my guest on the podcast. I know it's not really a rule, but I figure I might as well. Why not? So, anyway. So before I start, why don't I start by asking about how you grew up? Let's start by saying, where did you grow up?
I grew up in the eastern part of India in a state called West Bengal. Mm-hmm. So I was in a very small town. a college town much like this, West Lafayette, actually.
Oh, really?
So my dad taught there.
But okay. I thought you said, okay, hang on a second. Because you've told me before you grew up in Calcutta.
I was coming to that.
Oh,
so
okay, sorry.
I was in this small college town till the age of 3.
Till the age of 3, okay.
Yeah. Maybe 4, whatever. And then we moved to Kolkata, which is the capital of West Bengal. It's a big city.
Okay. Okay, so now tell me a little bit about like Calcutta, because I've never been. It's a big. The thing I know about it is big.
Yeah. So how do I even begin to describe that city? Well, it's maybe comparison's a better way. So let's say it's a lot like Midtown Chicago, a lot of it.
A lot like Midtown Chicago. I guess because you've been to Chicago, so that's how you have a reference.
Right, yeah. Well, I don't know how to describe it.
Okay.
But it's a big city, and it's a very old city. So that was the capital of British occupied India for a while. So the colony for a little bit, actually for a fair bit. So we have relics from that era. We have a lot of old stuff.
That's good.
And from my perspective, kind of cloudy skies.
Kind of cloudy skies. So growing up so before you moved to Calcutta, you got nice clear skies.
That's true. Yeah, I did.
And so that's relevant to. I guess you're starting to look ahead to my later questions because that's relevant to you being interested in astronomy.
Yeah, I mean that's all I can think of. So. The terrace being one of my favorite spots in my apartment complex, I used to go up there, and I remember getting annoyed so many times because all I could see was the Big Dipper, and
that was the one thing in the sky. Everything else was just either city lights or smog.
Yeah.
But okay, so Calcutta is where you grew up, and do you have a memory of when you first wanted to started to get interested in science? This is what happens when I don't have my questions written down. I asked the questions wrong. But anyways, do you have a memory of it?
No, that's a great question. So about science, I don't know. I guess my first encounter with science was when my dad first started teaching me about little things about mathematics, like how numbers work and all of those things. So I remember getting very annoyed when I was asked to mug up the multiplication tables. I was like, what is this? And then he broke it down for me. And then I was like, which is a feeling I still get sometimes, as I guess we all do. So
you're doing your multiplication tables and you're kind of like, I don't care, and you're just telling me to memorize some numbers.
Yes, exactly. What are these things? And it was, and then he makes me, he helps me work out the tables by myself, just by adding numbers, right? And then I see where this is coming from, and then I go, it's useful to just remember these numbers. Okay, I'm gonna do it. That's cool.
That's good. So it sounds like your dad was a good teacher.
Yeah, pretty much.
Getting your kids interested in memorizing their times tables is not always. It's not an easy feat, I don't think.
Yeah, and then he points out there are symmetries in this table, right? If you write them right, it's even more apparent. 9 times 7 is 63, and 7 times 9 is 63. And I was curious, why is that? And I add the numbers up, and then I see why. And that was a lot of fun.
Oh, that's cool. So you mentioned your dad already. So your parents in general, do you feel like they were big influences on you and your how you grew up and what you got interested in?
Yes, they absolutely were. So the great thing about my mom and dad is they always encouraged me to ask questions. My mom would sometimes get annoyed because, especially when I was young, because she had a lot to do, and all she gets done in half an hour is answer my questions. I bet that's gonna be annoying.
Right.
But yeah, so that's the first big part. And
Okay. And so, so generally, like they indulged your question asking.
yeah, very much so.
As much as of course the kid question asking can get annoying, but it's always good to hear when parents are willing to stick it out through that and indulge it. So then they encourage you in academics and going to college and stuff like that.
Yeah. So my dad always how do I say it? So he liked to teach me himself, and he took a more active role in my academics. So he's the one who introduced me to mathematics. Also, he would take me stargazing, sometimes share stories from his childhood. That's how I got interested in this whole thing. And
it's interesting. Remind me, what did your dad do again?
He's a professor of electrical engineering.
He's a professor of electrical engineering in India.
Yeah.
And so he is interesting that he also took you stargazing. I always think that's kind of cool. Like people who, and when you're an electrical engineer, there's no reason to care about astrophysics, right? But, I think science-minded people, well, I think everybody probably, but especially science-minded people still even if they have, their field has nothing to do with astronomy, like we're sort of we gravitate, if you will, towards that.
Yeah. Actually, I cannot speak for everyone, but with my dad, I think this was all the more reason, right? Because you don't get to look at or wonder about stars for your day job. So that's all the more reason, I think.
Right. And so, sorry, I lost my train of thought, but the point was that they were very encouraging. Oh yeah, they encouraged you to, in academics and going to college and that sort of thing.
Yeah. And my mom, she has this thing about little things in life where she will wonder about these little things and encourage me to ask questions about that. So I think I get a lot of that temperament from her as well.
Okay, so and so when you eventually went to college, you went to college in India, in Calcutta.
Yeah.
Okay, and so when did you come to? You first came to America to come to Purdue?
Yes.
Okay.
That's right.
So you got your did you get your master's in India?
No, I got my bachelor's in electrical engineering from India, and then I came to Purdue.
And you came to Purdue.
Yeah.
Okay. It's interesting. So the transition to coming to America from India, is there a different, first of all, there's going to be cultural differences, I'm sure. Is there anything that stood out to you in particular?
Let me think. Well, the first thing was I came from a pretty big city, and there was public transport everywhere and little shops everywhere, and then I come to West Lafayette and I'm like, I'm in the middle of nowhere.
Yeah.
That was a big thing, and I figured I found that people are in general nicer, especially when they don't know you. Of course, your friends and family, they're gonna be nice to you.
Right.
But in general, strangers, I found out they were nicer.
Right, it's more personal. Yeah, I guess that's true. Even in big cities in the U.S., I think strangers are pretty nice. But yeah, of course, I imagine in a city so big as Calcutta, you can kind of lose that. So that's cool. But yeah, the public transport, it's really funny. I was just talking to Sue Lee, and she was saying exactly the same thing from when she came here from Seoul, which is another huge city. Why is there no public transportation? So those are the big things, I guess. But then, so there also, in terms of the academic system, is there anything like when you were an undergrad I guess there's a transition from undergrad to grad school, but generally, is there anything you remember academically that was different in India than the U.S.?
I don't think it's going to be a fair comparison because it's undergrad school to grad school comparison. But I have had experience with the undergrad school here, as a teaching assistant. So I feel like the Indian education system does more during high school, so we get to learn a little bit more in high school, which is why there's but at college level that gap is not that it's not a lot between India and the US. So I feel like there's a bigger gap between high school education and undergrad education in the US as compared to India, which sometimes impedes things.
Yeah, so that was my vague understanding as well. Not just India, but between the U.S. and other places, that our high school was maybe lagged a bit, but then once you get to college, it evens out, or even can potentially, in many ways, we really excel once we get to college. The thing I notice when I get Indian students is they will call me sir a lot. And it kind of, a little bit annoys me. I'm like, just is that so? Culturally, is it? I guess is it a lot more formal, like with your relationship to professors in India?
Yeah. So that's funny. It is and it is not. I think. I think we get sir from the British.
Oh, okay.
Sir and ma'am, I guess.
Yeah, that makes sense.
We can't think of calling on professors anything else. Even though I've seen students share an intimate bond with their professors, so much so like this. I remember this undergrad friend who once saw this professor smoking, and he just walks up to him and he's like, "Can I smoke some too?" And they just shared that cigarette. I found that so funny, but he still called him sir.
He said, "Sir, can I bum a smoke?"
Yeah.
Okay, so that helps illustrate the idea. So then, okay, now do you think your experiences growing up kind of led you in the direction of astrophysics?
Let me think. So, like I said, I've been interested in the little things, how the physics of it works, how things work in general, and then there was stargazing, and then that somehow fueled this thing. So I kept buying more pop science books, and my parents encouraged that. So it sort of became a runway reaction.
Right. Once your parents see you're interested in that, then they'll go, "Oh, okay, this is what we should get him."
Yeah.
But then why astrophysics?
Because I thought it was cool, and that was just it at that point of time.
Right.
And I also started reading about it, not just stars, and I thought this was super interesting. Like how the pop science books are. They'll not start with the rigor initially, and it'll be about things that we haven't heard about in our daily lives. When something moves at close to the speed of light, it contracts.
Right.
Time slows down. So and pretty much soon you go into the realm of science fiction, all of that. So it seemed cool at the time.
Right. Yeah, I know. I read a lot of those books. But so, all right. So let me ask this: when do you feel like you learned how to be a scientist? Or have you? I hope you have.
Well, if I say no, you know who the joke's gonna be on.
Right, that's right. Make sure you say that you have learned how to be a scientist, because I'm the one who's supposed to teach you that. But maybe let's actually break it down more, since you're a more unique case because you just got your PhD, and most of the people listening maybe don't know what a PhD really means. It's kind of this obscure thing that we hold as like, oh, the really smart people get PhDs, and then they get to put doctor before their name. And what does that entail? What does it mean? What's the difference between that and other degrees? And what is
So after I got my master's, that was a lot of coursework too. Although here at Purdue we do both coursework and research at the same time, so you're also working towards your PhD at the same time you're working for your master's. But that is especially if you choose the non-thesis option, that is essentially just reading a bunch of books, working through some problems, and taking your exams.
That's the master's.
That's the master's and also the bachelor's.
And also the bachelor's is just books
yeah.
and homeworks and exams.
And some experiments if you're in an engineering field or most STEM fields, I think.
Most STEM fields, there'll be some experimental
right.
component to that. Yeah.
Yeah.
So that's the basic. That's bachelor's and master's degrees.
Yeah. That I don't know if that was ever my expectation, because I saw my dad working for his PhD.
Right.
So I guess that was not the expectation, but this was different. This was so different. So, this was all about reading up about something, and let's say, I don't know, reading up about supernovae, which are stellar explosions, and then you get an idea, you start to work on that idea based on some set of assumptions you make, and then you work at it, and suddenly everything goes wrong, and then you figure out those assumptions were incorrect, and then you start from a different set of assumptions, and it keeps on going until you find something that that you have reason to believe is right.
That is right, but also that is new.
That is new.
That
exactly.
We haven't figured out, that previously was unknown to humanity.
yeah. So there are no answers at the back of the book that you can compare against.
Right. You're supposed to write those answers. So that's So it's very different, and it's very vaguely defined, because we don't know what it is you're going to be studying, and what it is you're going to be solving, and what it is that's even the interesting thing to solve. You often don't really know whether a result's going to be interesting until you find out what that result is. so it's a lot of there's a lot of kind of wandering around looking at ideas and trying to see if there's something new to discover. But then, even that is that's a basic description of how the PhD works. But then, day to day, how does it work? Because, I think a lot of people are like, okay, you do research, you just try to figure something out, Why can't anybody just figure things out, right? What is it, do you have, how do you just go about that? And you say, people don't know how supernovae work. How do I learn how, how do you just figure something out like that?
Yeah, and I can speak for our specific field, I guess. But I think the general idea is just like this. You work with your set of assumptions and these experiments you have set up. Say, for example, I have this friend in the biological sciences who's, and of course I'm not going to be able to comment on that, but the idea is I heard that she was trying to work with these set of proteins. She was trying to do how these proteins reacted to a vaccine or something, and then she starts with an experiment expecting the set of results. She doesn't get them, so she thinks, well, there must be something wrong with the way I set up this problem. So she goes back to the initial conditions, how she set up the thing, and she works at it again. I found that very relatable, because that's essentially what we do as well. So we have an assumption for how a star is going to explode. We set up those conditions in say on pen and paper, or in our case the computer, and we evolve this state of the star again with pen and paper or with a computer. And then we see that the results we are getting, are they compliant with the observations that we have gotten of these explosions? If they're not, our story is wrong, and we get to start it
We get to try something else.
Yeah.
Try setting it up in a different way. Now, you're an astrophysicist now. You are now not only an astrophysicist, you now have a PhD. So let me ask you, what do you like most about your job?
The first thing that I can think of is there's always the thrill of the hunt, and there's always something interesting to look forward to, which is not always the case. Sometimes it's interesting and annoying, but it's always interesting.
It's always interesting.
And then the job is also very flexible, so I prefer to think most of the time, so I get to do that. think about my problems. Most of the time I get to do that, but there are some hours of the day I enjoy working more during. So like early morning is a great time to work for me. I get to do that, and also late night. I just tend to get more ideas during late night, so I get to do that.
Okay.
And kind of slack out
in the middle of the day.
In the middle
of
of
a
the day.
slack out period. That's fine. Yeah, I mean, it is nice. It is like the flexible schedule is very nice because everybody has different times when their brain is really active and able to work. So it's nice when you have that freedom. So, what do you not like about your job? Your advisor?
Am I allowed to say that now?
You can. Nothing I can do anymore.
No, I think I'm very thankful that I got to work with, and I'm very lucky that I got to work with you because it was not easy. You weren't here when I first arrived, and it took me some years here, and then you joined the department, and and I wasn't sure what I was walking into when I asked to join you.
Right.
But I'm thankful I did. But
good.
That's not what you asked. You
That's
asked
not
about.
what I asked.
You asked about what I didn't like about the job.
Say nice things about me, although you can do that at any time. But yes.
So, well, that's the thing about not liking my job. Sometimes I get really annoyed. So, because like you said, it's about discovering new knowledge, and some of these things I can't ask anyone about because they won't have the answers. So
right, nobody does.
Nobody does, and I gotta work them out for myself. And sometimes that gets a little annoying. I don't know what to do next,
right.
Or why is this thing not working? So it requires a lot of thought that sometimes annoys me, and sometimes I get zoned out just like that. And
really, I never get zoned out.
That's because you solved all your problems.
No.
And you have your PhD.
But you were saying I interrupted you.
No, that's fine. So sometimes I'll get zoned out and aloof, which is not always a good thing to do, like especially when you're with friends.
Right.
I mean, they're fairly short periods of time, but they'll happen to me.
Right. Your friends are like, what are you thinking about? It's just nothing. I'm just trying to figure out how this algorithm would work. And
yeah. I haven't. Never do that. Never do that. Never tell them what you're thinking about.
Never tell them what you're thinking about. Just be like, nothing. When you meet some a new student or fellow or colleague or astrophysicist, and they ask you what you work on, what do you tell them?
Right. Fellow astrophysicist sounds really specific. Do you want me to answer that question?
What would you say to somebody in your field?
Somebody in my field. Okay.
Yeah. Or vaguely in your field, someone in physics.
Okay, that's better because because if it's a fellow astrophysicist, I'm gonna say really specific things. And
that's okay. Either way, whatever. Just say a thing that you do.
Right. So I work on computational fluid dynamics, which is solving the equations governing fluid dynamics in a computer. Mm-hmm. And I try to model supernovae and remnants of supernovae. supernovae meaning explosions of stars.
So there's two pieces to that. One is computational fluid dynamics, and the other part is supernovae. So there's equations that describe fluid dynamics, and computational fluid dynamics means solving those equations not on pen and paper but using a computer, and basically starting with some fluid in some configuration and evolving it. So, and then people might think, how does that have anything to do with astrophysics? And what would your answer to that be?
Right. So for one thing, the equations of fluid dynamics govern most celestial objects. So, like the sun is a big ball of gas. So that would be governed by the equations of fluid dynamics. Of course, it would have additional physics to describe all that's going on in the sun, but it's still basically the equations of fluid dynamics. And so would be these galaxies which have a lot of gas swishing through them. So those would be governed by the equations of fluid dynamics too. And then sometimes these galaxies, the center of these galaxies will have huge black holes that will shoot out relativistic outflows that we call jets, really directional outflows. So unlike a spherical explosion, so those would be fluids as well. So all of these things are described by fluids.
Okay. And then in one example of something that's described by fluid dynamics that you already mentioned was supernovae.
Yes.
Right? So when these stars that are made of gas explode, then that explosion is also governed by these equations of fluid dynamics.
That's right, yeah.
And so you were saying you evolved these equations on the computer in order to understand how supernovae work, and in particular the things you called or I don't know, maybe you didn't say this phrase, but I will, supernova remnants. Okay, tell me about that.
Yeah, I was trying to avoid it so I don't have to explain that right away.
Okay.
But I'm glad you asked that question. So, stellar explosions are called supernovae, and when these things expand, say for 200 or 300 years, they make large structures, like large structures that can be studied or looked at by our telescopes. So unlike a supernova explosion, which is just in most cases speck, a really bright dot on the sky, this is an extended structure that's like 10 light years or so across.
Right. So it's had all this time to expand outward, and so it's gotten big enough that we can actually see it, we can image it with a telescope.
Yes, exactly.
And see an actual whole image of a supernova remnant.
Right.
And so one of the cool things I like about these supernova remnants is they're connected to historical supernovae, right?
Yes.
So my personal favorite supernova remnant is the Tycho supernova remnant, which is named after Tycho Brahe, who discovered it. You're going to remember the year. I won't remember the year. When did it go off?
1572.
1572. And so he discovered it back then, and then later now we can look at that same place in the sky and we can see this big ball of gas that expanded out.
Yes.
And so, what can we learn about them? Like, how do we understand supernova remnants and how they work?
So you mentioned Tycho's supernova remnant, and it's as close to a ball of gas as close to a ball as it gets, but not quite. So it's almost a ball, but it has these small scale structures on it, like the surface of a cauliflower. So it kind of looks like a cauliflower head.
Kind of looks like a cauliflower. So it's like if you look at the large scale and kind of blur it out, it looks almost perfectly spherical, as opposed to some supernova remnants that are, misshapen, weird things, like the Crab Nebula or Cassiopeia A is a bit weird shaped, but then but Tycho's remnant is really spherical, except like you said, on these small scales there's clumpy structures on smaller scales.
Yeah, so they say the Crab Nebula is shaped like a crab, which hence the name.
Is it?
I never understood why, but
okay, somebody very imaginative said that. I didn't realize that was why it was called the crab, because somebody thought it looked like a crab. But anyway.
But Tycho is not like that.
Tycho is not like that. It looks like a head of cauliflower. So that's the cauliflower nebula. But so then, okay, so what do we know? What does that teach us? That it's looks like a head of cauliflower. What does that say? Like, what's the difference between that? Why do some new remnants look like one thing and some look like a different thing?
Right. So, you expect so there are two types of supernova explosions. We call them core collapse supernova and thermonuclear supernova. So it's the latter kind that's expected to produce a mostly spherical remnant, and Tycho is an example of a thermonuclear supernova remnant. So it's mostly spherical, but when it expands, it's subject to a hydrodynamical instability. Of the same kind you would expect when you say pour milk into your coffee. So you start getting these swirls and eddies, these little pockets of fluid that move in circles. So you tend to get the same instability when your star expands against the ambient medium. So it forms these small scale structures, little eddies, and we believe those are the things you see in Tycho's remnant. The little small scale structures that make it look like a cauliflower head, those are actually the result of a hydrodynamic instability, a fluid instability.
Fluid instability that's present even in like your cup of coffee. And so the original supernova, all the gas that was originally in the star that's expanding out in the supernova, that's like the milk. And then the surrounding gas that it's colliding with, that's like the coffee.
That's the coffee, yeah, exactly.
And you can still get this instability, and it makes these clumpy structures.
Right, and these fluid instabilities are governed by how matter was distributed in the star before it exploded.
Okay.
And the structure of these instabilities can tell us a lot about what that density structure of the star was, how it was before it exploded, or maybe at the moment of explosion.
So if you can understand these fluid instabilities, because they're in detail, depends on where mass is in the star in the explosion, then that you can use that to trace back how mass was distributed in the original star, and then that tells you about what the original star was like. Back in 1572.
Exactly.
So what would you feel what was your contribution to that?
Right. So I helped figure out that this property exists, like the structure or the size of these small scale structures is indeed related to the structure of the star. And then I found out that other astronomers, especially people who deal with galaxy clusters, had devised a way to measure the size of these substructures just by looking at the image. And this seems like a trivial thing, but it's not. I mean, when you look at the image of Tycho's remnant, you feel like you can almost read off the size of these substructures just by like putting a ruler against the image or something.
Right.
But it's a little harder than that, and we don't do things in science quite that way.
Right.
Because it's like seeing what you want to see. If you put a ruler on the map,
you can just point to this thing. I mean, say that's what I think is going on, and just say like this size of this clump. That's the size that I think all the clumps are. So you have to do something a little bit more rigorous.
So we were in the same talk actually, and it made sense to us that we could use this technique. We could tailor it to our use.
Right. When you're saying we were in the same talk, there was this observer who came and visited Purdue, and she was presenting this, doing this talk on measuring turbulence in the gas. In the Milky Way, right?
Right. Intergalactic gas.
Intergalactic, not in the Milky Way. In intercluster medium. That's much bigger scales. But anyway, good. It's good that you remembered. But yes, looking at just ambient gas and seeing whether you could see evidence for turbulence.
Yes. So we also figured out that this fluid instability in supernova remnants. It's not. It doesn't behave like we expect these instabilities to behave. So these instabilities generate something we call turbulence. It's the same thing that you encounter on a bumpy flight. So the air around you is turbulent. And there's a specific property of this that was discovered by a Russian scientist in 1940s.
Right.
That we believe turbulence adheres to, but we found out that according to our remnant models, that this turbulence shouldn't exist. Such a property shouldn't exist for the remnants.
So when you say, so let's try to be a little bit less vague about it. So this guy Kolmogorov, who was in the 40s, who figured out like most of what we understand about turbulence still today, is basically made some predictions about how much energy should be at different length scales. So like you stir something at a large scale, and then that you make a big eddy, and that breaks up into smaller eddies, and then they break up into smaller eddies. And then the idea is he made a prediction just from pen and paper that how much energy will be at different length scales.
Yes.
And so and then what you found is that when you evolved a supernova remnant, and it looked like it was exhibiting this turbulence, but then it didn't have this same property, that like it didn't have power distributed at different length scales the way Kolmogorov predicted.
Right. So Professor Abigail Polin first suggested that this would be the case, and then I helped confirm that this would be the case using a different set of models. And then finally, when we applied this technique of measuring substructures from images to Tycho's remnant, when we did that for Tycho's remnant, we found out that's actually true. So
Tycho's remnant actually does, when you actually look at the actual remnant itself, not just your computer calculations, when you actually look at the remnant itself, it also doesn't obey Kolmogorov scalings. So
even though it looks very turbulent,
it looks very turbulent. Like some would say, if it's not obeying those laws, it doesn't count as turbulence. So that's very cool, crazy. So like, also, first of all, it's kind of like it's always crazy when you have some result that you have get out on your computer, and then you go and look at it, and then it does, and then the thing in reality, in nature, obeys the same rules that your thing in the computer did. So that's pretty cool.
You could call that an endpoint, because like.
But what else did he? Let me ask you this. So now that you've done this study, like relating to Tycho's remnant, what else is there to do now? So you've kind of explained how turbulence behaves in Tycho. Is there more to say, or is there more to work on?
Oh yeah, I think we're just beginning to scratch the surface of these things. So for one thing, I study computational fluid dynamics, but there's one more piece to this puzzle, which is these things, they're not just fluids, they're radiating fluids, they're radiating light, which is why, or electromagnetic waves, I should say, not just visible light.
That's what physicists call light, is electromagnetic waves.
So they're radiating light, and this light is also interacting with matter, which makes it a little more difficult to understand, and sometimes annoying. So we need to take a look at those things, because that's essentially what we are comparing against. We are not just comparing our fluid models to Tycho, because not everything that exists and makes worlds is bright. So what we see are only what's bright.
So then the point being that of course, because light is the only way we actually see these things, so we have to at least know a little bit about what the processes that produce that light.
Yes.
It's not good enough to just know what the fluid is doing, but how it's radiating and how that light will look to us.
Yes, I'm in particular interested in how X-ray emission from these remnants. So that's one thing I'm gonna be looking at. And then there's one more curious thing about these remnants. So when these stars, they had heavy elements in them when they exploded. They formed this at their core due to thermonuclear fusion. And so magnesium, silicon, iron, all of those things. So when you and these things, they emit at different wavelengths, like slightly different wavelengths in these supernova remnants. So when you look at these supernova remnants, but at different wavelengths, you see different elements. So when you look at say images of magnesium, sulfur, not sulfur, maybe magnesium, silicon, or iron, you see slightly different images, even for Tycho. So a perfectly spherical remnant.
That the material in it is just like the different elements seem to be distributed in different configurations.
Slightly different configurations, which is surprising because you would think they're all mixed up pretty well together.
Right. You would expect turbulence to kind of mix things up.
Yeah.
And so then why are they not all mixed up together?
Right. And when you even look at these images, you see that some of these elements form bigger clumps than the others, and you start to think,
that's interesting.
Why is that? Right?
Yeah. That's very surprising, because you would expect that all of them are following the same fluid equations, but then maybe there's something going on there to understand. Very cool. Why don't we do the final hard question, which is, in your opinion, why should we study astrophysics?
I don't know, maybe we should both answer this question.
We should both.
Well, I studied because it's at school, but I think there, in general, if that's what you're asking, there's a benefit for us as in mankind to be studying astrophysics and physics in general. So we have built all of these things around us by looking at the world around us, right? So all we have learned about the natural sciences comes from observing the earth around us.
Right.
Most of it, I should say. So, for example, someone sees a log rolling down the ground, and they get the idea of a wheel, or maybe it was a rock. I don't know.
But one way or another, science ultimately comes from inspiration from what we see.
Yeah. But there is only so much of the universe that we can observe on Earth. So there is stuff happening at like unimaginable length scales or energy scales or time scales, millions of years, that's just not observable here on Earth. Like, we don't get to those energies in our particle accelerators. So the only way to learn about those processes would be to look at where it's happening out there in the stars. So that's
where you'll find the most extreme environments
and the most extreme physics. Yeah,
it's the most things moving at within 99.9999% of the speed of light, or things that are like the densest materials imaginable as a neutron star. Like you're not going to make those things on Earth, or at least anytime soon. And so and so that's a very good answer. But and it's interesting to think about that fact, because we like to think, scientists like to think of ourselves as just like magical brains that can, just imagine anything. But really, ultimately, as humans, our imagination is very, is often limited by what we have seen before. It's very hard for us to imagine something we haven't seen before. And so when we do look at things like you say, like inspiration for the wheel doesn't just come out of nowhere. We have to see it. We have to see something like that, at least a little bit like that first, until we can get an inspiration.
Yeah, exactly. And it's even hard to believe things when we see them for the first time, right? And there are plenty of examples of this in science. I like to say, and I have no idea whether this is true, but I like to say, like,
physicists would never have guessed that liquids exist just from doing math. They might have figured out that solids exist or gases, but liquids are so weird that I don't think we would have predicted them ever, except that they're all over the place in our everyday experience, so we know that they exist.
Why do you say that?
But I know, I just find it, I feel like, yeah, it's that concept of that, we try to imagine we can predict anything, but you really do need some kind of frame of reference to do that.
I'm curious now. Why do you say we couldn't have predicted liquids?
Well, I think solids and gases behave in ways that are reasonably easy to describe. Like solids are the sort of a condensed state where everything is like as close to each other as you can get, and gases are just everything is free. The liquids are this weird somewhere in between state that is really hard to describe mathematically. I mean, you can describe fluid dynamics, but it's hard to like derive those equations mathematically for a liquid. And I know that because I had to teach statistical mechanics. So, but anyway, I firmly believe we would never have predicted liquids if we hadn't seen them first. I don't know how that would happen, but if there was some like gas people living in the sun that are made of entirely gas, they might have predicted that solids should exist, but they would never predict liquids. That's my totally unprovable theory. So I hope that was useful to somebody. All right. Well, anyway, thank you so much, Dr. Mandal, for joining us. It was a pleasure having you on, and I hope you'll talk with us again sometime.
Thanks again for having me.
I'm going to miss having Soham around. I'm so proud of how far he's come, and I'm sure we will continue to see great things from him. So thank you to Dr. Mandal for joining us, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. Music on the Astrophysics Podcast was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. Please check out her music if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.